Okay, well, welcome everyone, or almost everyone, and thank you, the new arrivals, for coming just in time for my lecture. I know that's what I think what many people wish for, like America on her birthday wished to hear a lecture about inverse theory, but KITP was closed, so we couldn't do one. And I know many of you have wished also to receive an inverse theory lecture for your birthday. But there's someone in the audience, actually, who gets to get an inverse theory lecture for her birthday, so we can all clap and wish Sana a happy birthday. And of course, I did that to give Thorsten time to come back. The lecture today is based quite a bit on the slides that Mark Panning used 2 years ago with quite a few additions of my own. I've tried to make the lecture perhaps less ambitious, so it's not like pulling from the literature to teach you guys things the way that Louise just masterfully demonstrated, but rather it's really to look at the basics and start from the very, very simplest examples of inverse problems to try to draw some, I guess, to build some intuition and make some heuristics for what can and cannot be done in an inverse problem. And hopefully by the end of the talk, if I've done my job right, you will have the tools needed to at least begin to critically evaluate seismic tomography papers or various other inferences, because inverse theories really underlies all inference in geophysics, because what it is it's a combination of approaches that we use in order to determine some physical quantities or physical models given a set of data. This can be done in many ways, but the one crucial ingredient that we must have in order to perform in order to use inverse theory or perform an inversion is we must be able to calculate data or predict data from a known model. So in other words, whatever that model may be, it might be seismic velocities in the Earth, or it might be some geochemical process. What you need to do is you need to be able to predict what you should observe if that were the case, or if that model was known. And the ingredients are usually physics, although not necessarily, and that's not meant to be a joke. We usually define the forward problem using physics, but sometimes we don't know what the physics is. And then we have a variety of approaches, and this is especially true if you want to go work for Google or for other kind of information, big data companies. They often have to figure out what their model is given the data, so they can create these generative processes that can produce data from through an unknown model. Essentially, the machine learns on its own how to predict data. We usually use linear algebra. Again, we don't have to. But what we use it for is to map between the model and the data domains. So what I would like for you to think is I would like to think of kind of like two planets. One planet is the model planet, and one planet is the data planet. And what we're interested in is going between these two planets in an efficient way, so then we don't die in between. And sometimes, although probably we should do this always, we should use probability and statistics to try to quantify uncertainty of our physical model determinations. In other words, it's not so meaningful to just know that I have a particular model. It's much more meaningful to think about how certain the various model parameters or model quantities are. And in fact, we cannot do hypothesis testing if we don't place uncertainty estimates on our models, because that's just the way it is. So I'm going to get back to this topic of types of forward problems, but here I just want to illustrate a very simple pair of forward problems. In one on the left, we have a linear problem, a simple a linear relationship between quantities x and quantities y. And this linear model here has only two parameters. It has a y-intercept, which is here called m2, and it has a slope, which is called m1. And for example, there are some linear problems in geophysics. One of them is, for example, to predict the gravity given the density of an object at a known location. So, for example, if you know you have an object somewhere, determining its density is a linear inverse problem. Another kind of a problem might be a nonlinear problem, which tends to be more common. So here I just have a simple one where I have sine, which of course I drew in PowerPoint, so it's not a sine. But it's sine plus some constant equals y. And an example of a nonlinear inverse problem, and we'll get to this in more detail later, is, for example, to predict seismic waveforms given a 3D velocity structure of the Earth. This is a nonlinear, there's a nonlinear relationship between the seismic structure and seismic waveforms. So the way that we typically formulate inverse problems is that we have some observations, and these observations, whether we want them to or not, they're always sampled in time and or space. That's just the way things are. And we usually lump these samples of the data into a vector, which we call the data vector. So that's this vector right here. We usually call it D, and in the rest of this presentation I will call it D. Just to confuse you. The physical quantities of interest, which we also express as some kind of a finite set of parameters that we have to infer. These parameters might define a continuous distribution. For example, the parameters might be the coefficients of spherical harmonics that you've seen before, in which case you could construct the velocity at any point in the Earth given a finite set of parameters. But again, we're determining a finite set of parameters given this sampled set of data. And these parameters we lump into a model vector, which we call M. And then the relationship between the data and the model. So in other words, how you go from being inside from a model to how do you predict data from a model? We predict it using this function g of m, and I will use g always. G of m need not be linear. It could be a nonlinear function. It could be complicated. It could be unknown. It could be difficult to quantify, etc. But you have to be able to compute g of m. And then, of course, the challenge of inverse theory is to go in this other direction, to close this loop between the two planets of model and data, and to go from the data planet back to the model planet. And the question marks here indicate that I will teach you how to do that. Okay, so let's start with a very simple problem. Let's say that you have a friend who's a geochemist, or you yourself are a geochemist, or maybe a mineral physicist, and you choose to go in a lab, and under some specified conditions, such as maybe temperature or pressure, here are the conditions. It's the independent variable. It's something that you set yourself. Under some pressure or some temperature or some concentration of some chemical, you make some kind of a measurement. That measurement might be the strain. That measurement might be some isotopic ratio, who knows. Anyway, you've done this 4 times because you're kind of, your friend is not so eager, a geochemist, and so she only made 4 measurements. And so each of these measurements represents a pair of quantities. One is the independent variable, and the other is this measured variable, right? This one you set, this one you measure. And what you have to do is you have to think about, okay, well, if I have these 4 measurements, what do they tell me? What am I trying to learn from making these 4 measurements? Am I trying to understand the parameters of some underlying relationship between the independent variable and the dependent variable? And what is that underlying relationship? Well, you might consider, for example, that maybe these 2 quantities ought to be due to some physical intuition that you have built up from your classes in physics or in chemistry. You might think that the relationship ought to be linear. In that case, you would say that what you want to do in the inverse problem is to determine the slope and the y-intercept of this line. However, that might not be the case. In fact, maybe the relationship ought to be some kind of a PowerPoint exponential. Which again doesn't look like an exponential, but and in fact, this one fits the data better. But again, the question is, what is really your expectation for the relationship between this dependent and this independent variable? So the fundamental question when we do in inverse problems is this question of parametrization. What quantities or parameters should we consider? Should we search for the slope and the y-intercept of this line, or should we instead search for the parameters that describe this exponential? So like I said, physical models may provide insights into how to parameterize a problem. If you know for sure, for example, let's say that you're measuring the force exerted by a spring, you're stretching the spring, you're measuring the force, you would expect that that relationship be linear, at least if infinitesimal strain theory, if the strains are infinitesimal, so that's Hooke's law, then you would expect this relationship to be linear. But in some other situation, for example, if this is attenuation and this is temperature, we've learned that this relationship should be exponential. So a physical insight should help you parameterize your problem. However, sometimes physical insight is not enough. For example, if you ask, how does seismic velocity vary inside the Earth? You might not know at what scales it varies. I mean, from what we learned in Louise's lecture, we know that it varies on all scales. So how do you go about parameterizing a problem like that? In that situation, sometimes we resort to preferring what's called the simplest model, the one with the fewest parameters that can still fit the data. I'm using very vague language here, and we're going to become much more precise in our language momentarily. There's something called the law of parsimony, which is actually, it's not the fruit. It's a very useful heuristic. In other words, it's a very useful guideline for how you should approach problems, but it is by no means a law. And in fact, this law of parsimony has led us astray in the past, but I guess the hope is that on average it'll lead us in the correct direction more often than it leads us astray. So the preference for a simpler model is often justified by invoking what's called Occam's razor. And in one paraphrase of some monk's statement, it is vain to do more with, it is vain to do with more what you can do with less. The more and the with are here flipped. Sorry, guys. So it is vain to do with more what you can do with less. So I guess if you're decorating your house, you should have fewer decorations than if you're decorating with more. But another approach or another justification for preferring simpler models is offered by Karl Popper, where he argues that a simpler model is actually more easily falsifiable, and because the challenge of science is to falsify theories, we should usually formulate theories that are simpler. So for example, if your theory for why the moon goes around the Earth is that it's carried by invisible unicorns, that theory is difficult to falsify because they're invisible, and therefore this kind of an approach would be would kind of bias you against a theory like that. And then I have this quote, which is by Enrico Fermi, and there's even a citation down here. This is Jessica Irving brought this to my attention. I remember my friend Johnny von Neumann used to say, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. So in other words, you should be careful about models that have lots and lots of parameters because they have a magic ability to reproduce whatever data you throw at them. And they might not be the ones that give you the most insight. So speaking of that, let's consider the first type of inverse problem, which we will call the underdetermined problem. So this is one of the favorite problems in high-impact publishing. We have one data point, and we cannot, with just a single data point, the idea is that you cannot simultaneously determine the y-intercept and the slope of a line, right? Because you could draw that line, but you could have drawn that line through it, and you could have drawn that line through this one point. This is really obvious, but it's obvious when you draw it like that, and it's less obvious when it's in part of some very complicated and sophisticated sounding machinery. In other words, what happens is that you have complete trade-off between the slope and the y-intercept. If you make the slope flatter, the y-intercept has to go up. If you make the slope steeper, the y-intercept has to go down. There's complete trade-off between 2 parameters. You cannot infer the value of one or the other uniquely. Instead, you can just infer their grouping. And so there could be this line, or of course, you might make a discovery by fitting that line to it and publish it in Nature. But not science, because science has statisticians reviewing your stuff. So that was an underdetermined problem. In other words, you don't have enough information to infer all the parameters you want to infer. You can have what's called an even determined problem. In an even determined problem, you have exactly the amount of information to infer the parameters you wish to infer. So for example, if we want to fit a line to 2 points, we can do so uniquely. In other words, there's only one line that goes through both of these points. And so from that line, we can determine the slope, m1, and the y-intercept, m2. If we wanted to fit some more complicated curve to these 2 points, we would again have an underdetermined problem, because that other more complicated curve would have more parameters. So if you have the equal number of model parameters and observations, you have what's called an even determined problem. So you would think, okay, great. Sorry, did I do this wrong? Yeah. So great. We went from having one point, and we're trying to fit a data to it, and then we had another point, and things got easier. So if you had a third point, things should get easier yet still, right? Because now you have 3 points, and all you have to get is 2 parameters. Well, that's not really the case, because once you have more data than model parameters, you have what's called an overdetermined problem, and then a whole other can of worms opens up. When you have more than 2 points, the line is not guaranteed to pass through all the points, unless they all happen to lie exactly on a line. So for example, here we have our 4 points that your lazy friend measured for you, and you have to fit a line to them. So the question is, where should you draw this line? Should you draw the line through these 2 points? How about those two? Those two? I know this is obvious. Well, maybe you should draw it like that, maybe, right? But I'm not telling you something very important. So what we want to be able to do is we want to objectively be able to answer the question, what line should be fit to these points? There's 4 of them, so I'm not going to fit them all. So what should I do? How can I objectively choose which line is best? Well, I mean, the intuition that we have is that we want to look at how well our line, how closely our line passes through these points. And we want to look for the line that's kind of the best at that. A line that minimizes these residuals, or the difference between the predicted value of the measure that you should measure and the actual measurement. So this line does a fairly good job. These little residuals between the prediction and the observation are fairly similar to one another. And what we want to do is we want to combine these residuals into some kind of an objective function, a function that's not subjective the way that we are, but a function that's objective, and it tries to tell us what is objectively the best fit. This function is also known, probably more commonly, as the cost function or the misfit function. Usually we want to minimize cost unless we're at an, what are those called? Added cost government contracts, where the more your cost goes up, the better. But usually we want to minimize cost, we want to minimize misfit, and we want to minimize this objective function. And in fact, we have a couple of choices there. We can minimize when we have, in a situation like this, we have not just one residual to minimize, but we have 4 residuals to minimize. In fact, for every data point, we will have a residual. So how do we combine these? Well, one way to combine them is to sum the absolute value of these residuals. So this is the difference between the observed jth point and the prediction for that jth point given the model. And you take that difference, you take the absolute value, and you sum them all up. And this one up here, this objective function, I'm going to use phi to signify the objective function. This one is called the least absolute residual, least absolute deviation, least absolute error, or least absolute value, or I will call it the L1 norm. So this is another choice that we have to make at the beginning of our inverse problem, is we have to decide what kind of an objective function are we going to minimize. A more commonly used misfit function, we will see in a second why this is the case, is called the L2 objective function. Here, instead of taking the absolute value of the residuals, we actually raise them to the second power. And what happens then is that the data that are outliers, in other words, that have high residuals, they have a stronger effect, because when you square that residual, that when you square a larger number, it becomes even more larger compared to the other numbers. And so this kind of emissive function tries to fit outliers much more so than the L1 norm, which tends to ignore outliers. So if your data is full of outliers, you probably shouldn't use it. This is also called the least squares because you're trying to minimize something that involves squares, so it's least squares. You can also take the L3 norm or the L4 norm, or you can keep going up until you get to the L infinity norm. In the L infinity norm, you take this residual and you raise it to the infinite power. And when that happens, the only thing that matters is the largest one, because that one will be so much bigger than all the others that all the other ones will not matter. So it's equivalent to just minimizing the maximum residual between the data and the prediction. What this approach, this L infinity norm, does is it produces something that's never terrible. So if you never want to be too far away from any given data point, you should use this approach. But you're also not going to be, in general, very close to any of the data. I mean, it depends on how much variability there is. We need a microphone up front. And while we wait for that, this method is often called the minimax method. And I'll pause, let that sink in. Okay.
So my question is, if a number smaller than 1 raised to infinity power is even smaller, right?
Yeah.
It's only a number larger than 1 raised to infinity power is even larger. So I think what you mean here is you have to normalize the d minus j
the next
to something.
Great point. So you're getting to something. These numbers are arbitrary, right? I could just rescale all the values, and then if they're less than 1, then if I square them, they're smaller. So what are these numbers with respect to? Well, we have to talk about what data uncertainty is before we can answer this very insightful question. You can imagine, for example, in this problem of fitting a line to 4 points, that if you know that one of these points was measured when you were drunk, you might not care so much that your line doesn't pass very closely to that point, because maybe you were more careless, or maybe you were upset because someone yelled at you and you weren't able to concentrate on a measurement. So if the error of one of the measurements is expected to be much larger than that of another, then you wouldn't expect the line to pass very closely to it. And in fact, you want your objective function to know. You don't want it to be ignorant. You want to tell it the information that you know. You want to tell it this measurement, it has a larger uncertainty. And you shouldn't count it as much as you count more accurate measurements. So what we need to really do to do an inverse problem is we need to assign uncertainty to our measurements. And so what I've done here is I've drawn, I guess, 2 sigma error bars on the side of each of these things. You'll see in a second. These error bars, well, I haven't yet said anything about how the errors are distributed, so these error bars just suggest the kind of variability you expect. If you were to repeat this measurement over and over and over and over and over again, you would expect the measurements to always lie within, let's say, or 95% of the time to lie within these within these error bars. And you can see that this is the measurement you made when you were drunk. Yeah, except in this problem, so Barbara brings up the important point that often when we make plots of one quantity versus another quantity, we're actually plotting 2 measured quantities. In this case, I have if you have 2 measured quantities, then your error bars would extend in both directions because both of the measurements come with error. However, in this case, I'm saying that one is a control variable, so you have like infinite, let's say, precision on your ability to set the temperature inside your diamond anvil cell, much like in reality. So that ends up being it. The math gets much trickier if you have to take into account the these variables. But you can do it, and you can read papers on it. I can refer you to them. So the point here was that, okay, good. So this is the line we fit before by I. But now that we know that this one sucks, we don't have to be that close to it, and we know this one's really precise, so we want to be closer to that one, so now our line has changed. In other words, our answer has changed as a result of just changing the uncertainty that we assign to the measurements. Very often, but not always, it is the case that these measurements themselves, the error on the measurements is distributed in some kind of a normal distribution. So it's normally distributed, in which case we can define a variance that's meaningful. And then that variance will tell us that, for example, if we repeat the measurement, I don't know, so if we repeat a measurement 100 times, 68 of the times, the repeat measurement will lie within one square root of this of the mean measurement. When that happens, when you know for sure that your error is distributed in this normal way, when it's a Gaussian distribution like this, then the correct objective function to use is the L2 misfit function. That is the optimal misfit function when the errors are normally distributed. So what you should do is use this one here, and then we have to actually square all the, we have to scale all the residuals by the variance. And this gets to Lee's question. Now when they're scaled to the variance, when this number is larger than 1, it means that your deviation between the prediction and the observation is statistically significant. It's significant. You're far away from where you should be. But if it's less than 1, you don't really want to worry about it. So as you square that number and it gets smaller, it doesn't really matter. Okay. So this is our linear problem. We have done a couple of things here. Yes? We've assigned uncertainties. We have assigned distributions to these uncertainties. And now Laurent asks the question.
Yeah. So you say that's the right, this L2 with the sigma square is the right way to do it. But before you told us that tries to actually fit through outliers.
Yes.
So you could still have an outlier even if the error for that outlier are normally distributed, right? Well, because that may be a point that is actually in error. So is there any sense where it would make, or is there any condition where it would make sense to use the uncertainty in the L1 norm?
If you know for sure that your errors are normally distributed, it is not the appropriate thing to do. However, what you're saying is true. Just because something is a 3 sigma variation from the mean doesn't mean it never happens. In fact, it means it happens sometimes. It just doesn't happen often. So you could just be a very unlucky geophysicist or inverse theorist, and you have to invert the data with an outlier. In that case, yeah, the L2 will give you the wrong answer. But if you were to repeat it, the next time it would give you the right answer. And if you did it 1,000 times, it would give you a better distribution or a better, more accurate appraisal of what the true model estimate is. Well, getting to that. One complication at a time. Anyone else have questions? Okay. So we did that. Sorry. Okay, so we're here. So now we have uncertainties. We have the distributions on the uncertainties. We know that they are normally distributed. We know that the sigmas are here. The variances, sigma squareds, are right here. Each measurement has its own uncertainty. And so what we want to do is we want to tell the inversion, don't care so much about the outlier. Don't care so much about the data that has high uncertainty, because it's not as high quality as the data with low uncertainty. So what you want to do is you want to take that uncertainty. You essentially take 1 over that uncertainty so that the large uncertainties become small numbers, and you essentially just rewrite your equation d equals gm, except each time you write it where you weigh each one of the equations by the inverse of the covariance matrix. So there's actually a missing inverse right here. So 1 over sigma squared, 1 over sigma squared, 1 over sigma squared, 1 over sigma squared on each one of these. And what I've done here is I've done a sleight of hand. As you can see, I've put all of these uncertainties in a matrix, this data covariance matrix, but I have populated the rest of the matrix, the off-diagonal elements, with zeros. And what that means is that I have assumed that the error on the measurements is uncorrelated. So it means that essentially the order in which you make the measurements doesn't matter. The data are independent one from another. The data uncertainty is independent from the data uncertainty on another measurement. And again, these should be 1 over. You see there's a -1 there. When we write this equation of a line in matrix notation, so the left-hand side just has the CD minus 1 times D, the data vector. The data vector are the 4 Y measurements. And it has to equal, again, this CD inverse matrix here. And then you have to be able to write these equations in matrix form. And the way you do that is you take your x values, x1, x2, x3, x4, and put them in a column. You put 1s in the other column. And your 2 model parameters are in a model vector, m1 and m2, so that the equations, if you read them one at a time, here you would get, for example, x1 times m1 plus m2, and then the whole thing times 1 over sigma squared 1 equals 1 over sigma squared 1 y1. And so what happens then is, since you're simultaneously solving 4 of these equations, some of them you made less important, you downweighed their importance by incorporating the uncertainty in this formulation right there. And then your misfit function, the equivalent of this in matrix notation is this right here. So you have a data minus g times m, so that's the prediction, transpose, and then multiplied by this inverse data covariance matrix. That's essentially equivalent to dividing each of these residuals by the variance corresponding to that measurement. And so this is your new misfit function. Okay? Yes, Juan.
So the variance, it's a 68% probability. I don't remember if things change, if it's better to use the variance or like a 90% probability. You know what I mean?
So what happens is, if you want to assign probabilities to this to quantities you obtain from this misfit function, you actually have to divide the misfit function by 2, and so you're correct. So if you assign unlikelihood, it would be 1 to the minus misfit function divided by 2. That would be does that answer your question?
Yeah. Absolutely.
That's where the 2 comes from if you're thinking in terms of probability.
No, I'm also thinking so when you do t-test for data and you try to assign a 95% probability interval, depends on the number of data, so it can change depending on many things. So it might be different using a 65% probability interval or a 95% probability interval or a 99% probability interval, and that might change. So for one point, your error is based on 100 measurements, and for another point, the point is based on 50 measurements. The intervals or the error might be different depending on the percentage or the probability interval that you're using.
As long as your relative variances between the different data are properly characterized, you don't have to worry about that. Okay? I mean, we can talk about it more, but I mean, it's a strong assumption that the stuff is normally distributed. In practice, it might be better to do something else. So we have this misfit function right here where we have the weighting by the uncertainty, and so I've written it up here, so it's just migrated from the bottom to the top, and my slides are getting cut off. So what we want to do is we want to minimize this misfit function right here, and when it's at a minimum, its first derivative is going to be 0, and its second derivative will be happy, it's going to be positive. And so what you can look for is when does the first derivative with respect to all the model parameters of this function right here equal 0. And if you do that, you will find that the model for which this derivative equals 0, and that's a minimum, is this model right here. So this is the algebraic expression for the model that you should obtain using least squares minimization. So this guy, mest, model estimate, is the estimate which minimizes this misfit function, this L2 misfit function up there. So what you can see, it has a couple of ingredients. They kind of repeat over and over again. It has this matrix G, which was just those x's and 1s. In other words, it is the matrix that defines how you map from the model to the data space. You weight that matrix by this data covariance. You take the inverse, and then you have another one right here. That's again that matrix. The transpose of the matrix takes you from data to model. The matrix takes you from model to data. So they kind of appear always in pairs. So this ms is the least squares estimate of model parameters in the general parlance that people use. So now we want to ask a question, which is how confident are we in our inferences of this mest, in our inferences of the model parameters? In this case, it's just two model parameters. One is the slope, one is the y-intercept. How confident are we in those inferences? Well, we can actually evaluate the uncertainty of the model parameters using what's called the posterior model covariance matrix, C sub m, with a little tilde to tell you that it's special. Because there's one that doesn't have the special. But before that, let's build some intuition, because if we start looking at this matrix, it might not give us the intuition that we desire. So here I put two even determined problems. We have two data points, and we're trying to fit a line through them. In this case, the data points come with slightly larger uncertainty than in this case. So I ask you, which scenario, left or right, will yield a less uncertain estimate of slope? Someone can shout out. Less uncertain means more certain, more confident. The right. Everyone says right. It's one of the few times that the right is right. Political statement. So over here we have lower uncertainty. So your intuition is perfectly correct. If you go ahead and calculate this model covariance matrix, this posterior model covariance matrix, you will find that in fact your uncertainties are lower if you use these measurements back here. And if you look at this thing right here, you will see that the well, actually, I'll explain that in a second because it'll be clearer on the next slide. So yes, it's better to use the one on the right. The objective function is more affected by slope variations when you have small uncertainties, because those deviations get divided by a smaller number, so they become bigger, they get squared, they become even bigger. So small variations in slope are going to affect your misfit function a lot, and therefore more accurate data tends to yield more reliable estimates of parameters. This is very intuitive, but it's important, and it's important that our theory lines up with that expectation. The next question we might have is the following one. So here we have, again, two even determined problems. We have two data points. Here they're widely separated. Here they're closely separated, but they have the same uncertainty. Which scenario, left or right, will yield a less uncertain estimate of slope? Left. Good. So the left is correct. And why is that the case? Why were you so quickly able to answer this question? Well, the way that you can think about it is that these guys are separated widely, which means that slope variations are going to affect the prediction of one versus the other more than if the data points are close together, right? Because the slope gets multiplied by their horizontal distance to give you the prediction. And in terms of an inverse theory parlance, what you can say is that this data here is more sensitive to the slope variation than this data. It's not that the data is better measured. It's not that it's better data. It's just more sensitive to that parameter. Okay? So when you have parameters to which you're more sensitive, those parameters tend to be better estimated. Tolu, we need a mic for Tolu. So what you mean? No, we need a mic for you. Iron fist. Okay.
So what you mean is set of data, not like type of flavor of data, like from one lab or another. You just mean this set of data collected.
Yeah, you might be presented as an experimentalist. You might be presented with the challenge of, should I measure this quantity or should I measure that quantity? Well, if one of those quantities, if the thing that you're ultimately interested in is more sensitive to that quantity, you should measure the quantity to which it's more sensitive. But yeah. For example, if we look back to the lecture on density and VS, the modes are more sensitive to VS. So they're going to give you better estimates of VS than they will to density. That's why we still argue about density, but we don't really argue about VS. So let's take a look at what this special matrix looks like. This matrix is given by GT CD minus 1G, all inverse. So the way you can think about it is that the larger you make the variances, the more uncertain your data. When you take the inverse of that, they become smaller, but then this becomes larger again. So then the uncertainties on the model parameters become larger. It kind of scales with the data uncertainty. And this guy is a 2x2 matrix because you have two model parameters. So it's going to always have the dimension of model parameters by model parameters. Along the diagonal of this model covariance matrix, you will have the variances on your inferences of slope and y-intercept. So this guy here tells you what is the variance of that slope estimate that I gave you. This one tells you what is the variance. Oops, wait, I think this is animated. Hold on. Variance of the slope estimate right there. Variance of the y-intercept estimate. And this one here is the standard deviation of the slope times the standard deviation of the y-intercept times this rho. That's not a typo. The rho is the correlation between these two estimates. In other words, how much will one quantity change when you change the other one? How much do these two parameters trade off? In our example where we had a single point and we tried to fit a line, this rho would be 1. They have perfect trade-off with one another. If one goes up, the other one. No, rho would be -1 because they kind of oppositely trade off, right? If they traded together, if they varied together, it would be 1. If they didn't affect one another, it would be 0. You want these off-diagonal terms to be 0-ish because that means you have fewer trade-offs in your inferences. Now, this is really important, and this is kind of a slightly more nuanced point. This posterior model covariance matrix, what it does is, you see, I'm telling you this is a variance, and this is a variance, and this is a covariance. What it's telling you is it's really approximating the true uncertainty by what's called a generalized Gaussian distribution. In other words, it's like fitting like a Gaussian that you can kind of squeeze and stretch to that most likely point and giving you an uncertainty estimate in that way. And this is sometimes okay, but sometimes it's not okay. So it's something to keep in mind. And we'll talk a little bit more about when it is and when it is not okay. So now I'm going to kind of jump into something that's a bit more abstract than this. So here we had actual numbers. We had a slope and a y-intercept of a line. But it's really tedious to solve each problem one by one. And you'll get bored, and you don't even know why you're doing this. So let's think really conceptually, really big picture. Let's imagine that all the data you measured is represented kind of schematically on this y-axis here. So it could be a single data point, or it could be a billion data points of different types even. But what I'm showing here is then this is the data space. Remember, it's like the two planets. This is your position on the data planet. And that data has some uncertainty. So it has a region that has high likelihood and a region that has low likelihood. So I drew this Gaussian kind of distribution here. And what I've done is I've shaded, as I learned to use the gradient tool in PowerPoint, which is really cool. I shaded this region here according to its likelihood. So this is low likelihood is where it's this kind of bluish grayish color, and it's red when it's high likelihood. Okay, so in a linear problem, the relationship between the data and the model, which is this other axis, so it's the other planet, that relationship is a straight line that's defined by d equals g times m. The reason here we don't have g of m is that any linear mapping from one kind of vector, the model vector, to the data vector can be written by a matrix multiplication. So why write it g of m when we can write it g times m? So this is a matrix multiplication. So this is our constraint. This is all the physics and the modeling, kind of the physical model that you have. And so given this physical model and this distribution of data, what we can do is we can actually see that here we have low likelihood. Here we have high likelihood, right? We're in the red region. Here we have low likelihood. So we can actually map it down. So we have low likelihood model regions, low likelihood model regions, high likelihood model regions. The maximum is what we would call M-est. It's the estimated model, the least squares solution that we would have in this case. And so we then also get a uncertainty on the model parameters. This would be described by that CM tilde matrix, okay? So what we did is we went from a schematic representation of where the data is through a schematic representation of the relationship between data and model, and then we made an inference of what the model should look like given that constraint. And this figure will come back a number of times to teach us things about nonlinear problems and data uncertainty well, no, this already has data uncertainty. Modelization uncertainty, as the Europeans say. Common complication. Oh, okay. So far we've worked with this very simple problem that's either even determined or overdetermined. But in reality, in many problems of interest, we have what are called mixed determined problems. In these mixed determined problems, some parameters are well constrained. They might be excellently constrained, and other parameters are poorly, or in some cases, completely unconstrained. In other words, you have no ability to uniquely resolve the value of one of the model parameters. But you can do a really good job with the others. But you can't kind of strip out the one from the others, perhaps. So when that happens, the determinant of this matrix, so hold on. In our solutions, we always had to take the inverse of this matrix here. But when you have this mixed determinant problem and one of the parameters is completely unconstrained, the determinant of that matrix becomes 0, and you cannot take the inverse of it. The inverse doesn't exist. The matrix becomes singular. This guy here, we sometimes call G minus G. It's like the generalized inverse. Anyway, this notation will come up later in the lecture. So when this matrix doesn't exist, what do you do? When that matrix doesn't exist, the problem is telling you that there's an insufficient number of linearly independent constraints to determine the unknowns. In other words, you don't have enough independent data to answer your question that you're asking the inverse problem. And so what do we do in that case? Okay. So what we do then is we use what's called explicit regularization. So regularization is you take this problem that's like, oh my God, what do I do? I can't invert it. And you make it regular, so you can invert it. So that's why it's called regularization. Regularization is the procedure by which we modify our problem to ensure that this generalized inverse does exist. So we're going to have to fiddle with the problem. But how do we fiddle with it, and what are the common approaches for fiddling with it? Our parameterization itself is fiddling with it. For example, you might just throw out that model parameter that's giving you trouble, that model parameter you can't constrain. So in some sense, our model parameterization already is an implicit form of regularization. By decreasing the number of model parameters that we have in our parameterization, we might solve the problem and regularize it. We might be able to invert for the solution. But sometimes, and so, for example, we can reduce the number, or if you think about in seismic parlance, for example, instead of asking for what the structure is at some small length scale, you ask what is the kind of largest wavelength structure on the Earth. So you're simplifying the question that you're asking, and that's one way of regularizing. However, sometimes you can't do that, or you choose not to do that. And in that case, you have to explicitly fiddle with the problem by introducing additional equations. So you take the equations that you have, which form the relationship between data and model parameters, and then you just make up new equations. Okay? Literally, you write down other equations that you need to have. And there are two common sets of new equations that you do. Sometimes we add equations that essentially tell the inversion that it wants to find a model that's close to some reference model. In other words, it wants the deviation of the model parameters from some values that you came to believe through some process, either through the process of learning or guessing. You want your solution to be close to that reference model. The reference model here is shown right here. And so we have your actual model minus the reference model transposed times the other one. This is essentially what the length squared of that vector is, of the differences. And so what you want to do is you want to minimize this guy in addition to the typical thing, which is that you want your residuals to be minimized. This procedure is called norm damping. Sometimes you don't want to do that. Sometimes you want your model parameters to be able to go very far from your starting guess. And in that case, you might do something different. You might introduce what's called smoothing, because what it does is it minimizes the roughness. In other words, it minimizes the size of the first derivative of the model parameters or the second derivative. And in this case, the model parameters really have to define some kind of a physical space or physical quantity, because taking spatial derivatives of something that's not a physical quantity or spatial quantity is not the best idea. So in that case, we want to minimize this dm. I'll show you what the form of d is in a second, in addition to minimizing this residuals. Okay? So these are two common approaches. Now let's see how this works in reality. Hold on. Okay. So here's our equations we started with for the line. We can add another equation which says that the model parameter 1 should be 0 and the model parameter 2 should be 0. So that's like obviously wrong, but whatever, you can just put it in. And then you can put this D matrix here, which is that the difference between this one and this one should also be 0. These are kind of silly example because the slope and the y-intercept of a line need not be like comparable to one another. But this is just to illustrate how you would do this in another problem. So now instead of having 4 equations, you have a total of 7 equations, right? And when you do your least square minimization, you find that there's these 2 additional terms that appear in this matrix that you're trying to invert. The 2 additional terms are this I, which is just the identity matrix, multiplied by some lambda 1 parameter, which I haven't told you about yet. And the other one is dtd, which is multiplied by some other scalar lambda 2. And so you add these guys, and now you hope that you've added enough so that the inverse of this matrix exists and that you can solve your problem. So how do you choose how much of this lambda 1 and this lambda 2 to add? Well, often what is done is what's called an L-curve analysis, although this is not always done, but sometimes it's done. And what the idea is, the more you add these made-up equations that you made up, the less you're going to be able to fit the data. So the more you add, the more of these equations you add, or the more you tell the inversion to care about these equations, the more your data misfit will grow. And this here is just a PowerPoint thing. And of course, the more you do that, the more your size or roughness is going to decrease. And sometimes there's this sweet spot where you've decreased your model size and your model roughness, but you haven't really messed up your data fit yet. And so then you would choose your lambda 1 and lambda 2 to be somewhere here, where you smoothed the solution or decreased the size of the solution, but you haven't messed up your ability to predict the data yet. And so that is sometimes how this damping is done. Another way to do the damping is to really forget about this way of forming equations and instead try to construct a model covariance matrix, just like the one we got from the inversion, but this time you try to construct a model covariance matrix that is based on your prior knowledge. So this one is called the prior model covariance matrix C sub m, and he's the ignorant cousin of C, like crown m, because he hasn't yet learned about the data. You're not allowed to tell it about the data when you write this guy down. You have to use some physical intuition. For example, you might know that a quantity should be between, let's say, 1 and 2. So you could then define that this model covariance matrix, you can say that the variance of that of that parameter should be like 0.25 or something like that. But the way that this model covariance matrix, so you define it ahead of time. You define the variance on the model parameter you expect for one model parameter, for another model parameter. You define this correlation between the two of them, the covariance between the two of them, and you add this matrix just like you did with the other matrix to this GT-CDG guy, and you hope that now it can have an inverse because you added it. And when you do this, you also modify what your posterior model covariance is as well. So you modify both the model estimate and the uncertainty on your model estimate. So let's view that effect in our, yes?
That if you go back to the previous equation, we don't need to add something analogous to lambda 1 in front of the cm to the minus 1?
You are doing something equivalently by choosing essentially a scale on these guys. But I guess the conceptual distinction I wanted to draw is that in one case, these lambda 1 and lambda 2 are just parameters you kind of like throw at the problem, whereas in this formulation, your writing down these quantities comes from some prior knowledge. So you know, okay, this quantity should have this amount of variation or not.
Ved, is it fair to say that these lambdas are positive numbers generally?
Sorry, these ones?
Yes.
Yeah, I mean, it wouldn't really matter. So if you did, well, I guess because, yeah, these guys always have to be positive. You're right. These guys always have to be positive because they get squared. So, yeah, they should be positive. Sorry. But you could have defined this matrix in some other stupider way. Yeah. Which is probably how I do it in my inversion. Okay. So let's look at this effective regularization. So again, we have our data. The red is high likelihood region. We had now we introduce a prior. So before we only started with this, but now we start with a prior expectation. I expect my model to be right here, and I think that my uncertainties on that expectation are indicated by these blue shadings. So now what you've done is you've kind of outlined a region of space, both in data and in model, where you expect your answer to lie. So now instead of looking all over the red thing, you're looking really within the green circle. Now you add your linear constraint between the data and the model vectors, and now you go along that line. You have low likelihood here, and you have kind of maximum likelihood right here, right? And then it goes again weaker, weaker, weaker. Okay? So now if you draw that other distribution, this is the solution that you would get. Okay? And that solution is distinct from the solution that we got previously. So the previous solution was here, because that's where the maximum was encountered by this d equals gm line. But now the maximum has been shifted by the introduction of the prior information. So introducing prior information will change what inference you make on the model. So it's like you should be careful about doing it, because you are really influencing what answer you get when you add this prior information. And this is, I think, a nice kind of visual way of conceptually seeing why that's the case. So now let's talk a little bit about the effect of modeling error. So in other words, what happens if this line d equals gm is not very well known? Sometimes we cannot compute that relationship between the data and the model perfectly accurately. Sometimes we have to do it through approximations. And here are some common approximations that are used in seismology. Here's a very esoteric one that's close to my heart, which is, for example, let's say that you're considering this wave SS. So it's a wave that leaves the earthquake, it bounces at the surface once, and it goes out here. And you want to use, for example, the travel time of this wave to figure out something about the structure between the receiver and the source. Well, to do that, you have to know where the wave is sensitive, right? You have to know to what parameters of Earth structure, these, you can think of them as these pixels, to what parameters is that wave sensitive? Well, one way of computing that sensitivity function, or also known as a Fréchet kernel, is by coupling, using normal modes that Miyake told you about and Jessica told you about, and then considering coupling along one of the branches, one of the dispersion branches of those normal modes. And when you do that, you build up a sensitivity that looks like this. So it's high here at the bottom near the turning point, and it's lower up here, but you can see that it doesn't vary with position. So these two things are equivalent. One thing is like a coupling in the mode space, and the other thing is like physical space sensitivity. But this is what's called a path average approximation, or a long branch coupling approximation that to this sensitivity of this wave. And you could do the same one for an S wave that diffracts along the core. That's called S stiff. In that case, the sensitivity looks like that, and you can see it's even more absurd because it tells you that you're sensitive down here and your wave is nowhere close to that. Okay, so that would be an approximation that introduces some kind of error in your modelization. You can fix that by, for example, accounting for a cross-branch coupling, and then you build up things like this. So this seems to follow the sensitivity of the wave a little bit more accurately than this approximation there. So that's like one way in which we seismologists sometimes futz with the problem and introduce errors. Another thing you might do is you might use any perturbation theory instead of some fully numerical approach, like, for example, the spectral element method. That would be another way you could add some uncertainty. Or you might use rays computed in a 1D Earth. In other words, you might assume that the Earth's velocity varies only with depth, compute how the ray paths should go through the Earth, but then have the velocities change with location and not recompute your ray paths. That would be another source of uncertainty. So what we want to know is we want to know what is the effect of this forward modeling error on our inferences. And here we go to a very similar kind of diagram, except now our relationship between data and model is not linear. I drew it like that. Again, we had a prior on the model. We had a prior on the data. In other words, we said something about what the data uncertainty is, what the model you expect to be, and then you have this region here which is like that green circle before. And if your uncertainty on the predicted data, it just ends up kind of blurring this line between the data and the model. What it'll do is when you compute your uncertainty in the model space, instead of having this nice red distribution here, you get this blue one, which you see is wider. And the reason it's wider is because now you're kind of convolving the width of this line with the width of this distribution. And so in other words, by adding this modeling error or modeling uncertainty, it's perfectly equivalent to increasing the errors on the data measurements. Okay? So in one way of taking account for it would be to have your data covariance matrix and add an additional covariance matrix which quantifies your uncertainty due to your modeling, and then you add these two matrices and take the inverse. And that essentially it's like you're sullying your data with your forward modeling procedure.
And everything up to now, again, the uncertainties are Gaussian?
Yeah, the uncertainties on everything are Gaussian, except here. Here, this sketch here is saying that it's not just that your theoretical error, your approximation introduced some Gaussian error on your predictions, but in fact, you completely drew the wrong line. This is the real line describing the relationship between data and model, and instead you drew this blue line. And if you draw the wrong line, you're just going to get the wrong model. This is the model you would get with that. Okay? So by improperly computing your forward problem, you can either reduce your ability to resolve model parameters. That's the best thing that can happen. Or the worst thing that can happen is you just get the wrong answer. So that would be this systematic bias in your model estimate. Now let's go through various. Does anyone have any questions? Now we're kind of going into a different topic. Okay. What are the different types of inverse problems? The problem that we've really talked about the most so far is this linear problem. So this is a figure that's taken from Tarantola. In fact, all of the other figures were kind of inspired by this figure. Here again we have a data, kind of a schematic representation of the data planet, the model planet, the relationship between the data and the model from the model prior and the data prior. In other words, how uncertain your data measurements are and what are they. And now you have a relationship between the data and the model which is linear, so we can write it as a matrix multiplication. It defines this line, and then we go along that line and we figure out what the highest likelihood region is, and we collapse it down here into the model space, and that's our answer with the uncertainties in the model space. This is a great problem. Least squares works if your data uncertainty is Gaussian, and this CM tilde is accurate. In other words, it tells you it provides a accurate description of what the true uncertainty on your model estimates is. This kind of a problem here, you can see that the relationship between data and model is not linear. It's not a line, but it's not that bad. So what we would say is that this is linearizable around the starting model. So this is the model that you started with. How do we know that? Well, this distribution is peaked right here. So that means your prior most likely assignment to the model was right here. You start there, and you just pretend that the model is linear. And you move on this blue line, and you're not that far off from the model. When you infer your model, you're not that far off from what you would have gotten if you actually followed this curve. But it gets worse. You might have a problem that's even more strongly nonlinear. That would be linearizable around the most likely model. In other words, here, this is your most likely model, right? And around that location, you might be able to linearize the relationship between the data and the model. But if you go further away, it doesn't work. And if you started over here, if you linearized here at the starting model, you would have made a line that was like that, right? So you wouldn't have gotten up there. You would have been completely wrong. Okay? So this is a more strongly nonlinear problem. Once you get there, you have to use what are called iterative techniques. So you must iterate. You must kind of start here, go here, go here, go here. Eventually you find this. Then you can linearize and find your uncertainty. And this CM posterior model covariance might be okay, but you have no guarantee that it's accurate representation of the model uncertainty. Then you might have something that's even worse. So here you have the relationship between data and model is completely nonlinear, and it's not just nonlinear, but it actually crosses this likely field twice. It crosses it here, and it crosses it here. So you actually have a bimodal distribution on the model parameters. There are two possible kinds of solutions. There's this kind of solution with this uncertainty, and there's this kind of solution, and there's this uncertainty. And they're both equally good. When this happens, you cannot use the approaches that I was telling you about. This model covariance matrix is woefully invalid. Remember, it only describes a single Gaussian, so it would have completely missed the other Gaussian. So it's terrible. Don't use it. And you should really not use least squares iterative minimization for these kinds of problems. Instead, you can use RJMCMC or other such techniques, and you can talk to Chow or Tolu about them. That's what we've been up to at Maryland. And then, of course, you have this problem, which I call the Trumpian or Brexistential problem. And essentially, nothing will work. You should give up and get a drink. One of the best Brexit posts was pub, ? That was the response to the Brexit vote. So that's kind of the response. If you're confronted with a problem like this, your geochemist friend tells you, oh, this is my problem, but I really want you to solve it for me. You can say, do you want to go to a pub? But when things are not that bad, so when they're kind of like in this regime, you can still do a good job. But then you have to use what are called model space search approaches. So when the relationship between data and model is nonlinear, the linear approach can be inadequate. In other words, you might get stuck in a local minimum, you might only see one side of the solution, or you might have a completely inaccurate representation of what your uncertainty on the model parameter estimation is. But we have these current approaches that explore the model space. So you can talk to Chow. You saw his poster. I guess Tolu's poster's on Thursday. Lots of people do this. It's really exciting for me, so I'm like plugging it in here. One of the nice things about these model space searches is they kind of walk around that model planet. They go around. They're like the Mars rover, but they move hopefully slightly more quickly, but possibly slower. And what they do is at each model, they tell you, okay, well, this model predicts this data. How likely is that? Okay, well, that's the likelihood for this model. And you keep going like that across the planet. And you can map out what the range of possible models is. And you don't need to introduce any regularization because there's no inversion anywhere. You're just forward modeling every time. So it eliminates the need for regularization, which means that you won't have as biased estimates of model parameters. Sometimes these models can actually jump between different, so sometimes it can like go inside the planet or move into like a higher dimensional space. In other words, they change the parametrizations of the models. Like the boxes might get smaller, or you might create a new box or delete a box or something like that. Those are called transdimensional methods, and those are exciting. Sometimes these methods also estimate the data uncertainty. Like if you don't know what the data uncertainty is, they can add that as a parameter in the inversion. Then they're called hierarchical. And finally, what these models in general do is instead of what these approaches in general do, instead of allowing you a single model, they create a whole ensemble of models. In other words, millions and millions and millions of models that you can then analyze to figure out what the uncertainty is and what the takeaway points are that you can really rely on. So I'll conclude my talk by going through the tomographic problem just because it's something that's dear to me. Here we have pink triangles, which always represent seismic stations, and we have some green stars, and we have these two structures. We have this elongated fast structure, which is clearly a slab, and then here we have this slow structure, which is clearly some kind of recycled crust in the upper mantle, which is probably EM1 or EM2. So this earthquake might be observed at this station. In other words, waves that go from this earthquake might be observed at this station. Because they go through this fast region, they're going to look fast. And these waves are also going to look fast. In other words, they'll arrive quickly. And then these guys will be super fast because they went almost the whole way through the fast structure, right? But then there's going to be a lot of other paths that are kind of neutral. Like they go through this background stuff, and so they go at some whatever average velocity is. And then you're going to have some other paths that are slow. And I didn't draw all the possible paths because that would get very tedious, and I was running out of time. So what we do is we take these observations of, let's say, travel times that are observed at these different stations for each of these events. So it could be hundreds or thousands. Right now, for example, the latest model with P-wave travel times that my postdoc Scott Burdick made has about 13 million of these. So you just take all 13 million of them and you put them in a vector. And you call that the data vector. It has n entries, where n could be 10 or millions. And then you have to say, okay, well, I have this D guy. I know my next ingredient is how do I predict the travel times given some model. So, for example, we might choose to parameterize this problem into a bunch of boxes. We have to choose parameters. We have to do a parameterization of some kind. And this parameterization, here I drew, I think, 17 by 17, unless I miscounted. If it's 17 by 17, I have 289 boxes. So the model vector M has 289 entries. It's just a column vector with 289 entries. And each entry is actually the slowness or the inverse of velocity of each box. So in other words, if your velocity is 10, your slowness is 1 over 10. If your velocity is 5, it's 1 over 5. And so what then you can do is you can write an equation like this. You have the data, the travel times from this of a particular wave J. And what it is it's the sum. So here I have used Einstein summation notation without actually drawing the sum sign. So what I've done is I've taken all the boxes that this wave goes through, and I've multiplied the slownesses in those boxes by the path length or the path distance that that wave J spends in box K. So essentially it's like how long is this line right there inside this box, right? And you do that for all the boxes and all the rays, and you can imagine you have this giant matrix. It would be 13 million by 289. And most of it will be zeros because most rays don't go through most boxes, right? But there's a problem. So here's a beautiful animation that Mike Thorne made where he did finite differences to really just illustrate Snell's law. And what he's doing here is he has a wave here that starts. You can see the wave is transmitting through. And it goes from a medium with velocity 6 to a medium with velocity 8. And what you can see is that the rays actually change their path, right? So is that a problem for the way that I wrote the problem? I wrote it as a linear problem, right? In other words, I wrote G here, but I don't know how long the wave goes through a box because I don't know what the velocities in the boxes are, right? So this is not a linear problem. We have to actually linearize it. So we linearize this problem. So the path depends on the slowness. And so what we do is we have to linearize. So we can either linearize from some starting model that someone else gave to us, or we can start anywhere and just constantly iterate, keep on linearizing, updating the model, and recomputing the paths, and so on and so forth. So what we would do then is we would write the data vector as the difference between the observed and the predicted time in that model. The model is the difference in the slowness between, in a box versus what we have started with, this VK0. And this GJK must be computed in this model or even at each iteration. In other words, as you iteratively solve, you just have to keep on computing your ray paths. So in other words, even the simplest tomographic problem is not linear. The resolution analysis. So how do we, let's say that we do this procedure of linearization, and then we want to say, well, how good is the model that I get? What features of that model might I be able to trust, and what features should I not trust? Well, I already taught you that you can take a look at this model covariance matrix. So you can literally look at what the variance is of each of the inferences of slowness in each box. And you can even map out which box slownesses trade off with which other box slownesses. But it's kind of hard, because that's going to be a 289 by 289 matrix. And your brain, or at least my brain, is incapable of simultaneously kind of digesting all those trade-offs between all those 289 parameters. So what we often do is we actually put in some input structures and see what kind of a structure comes out. So we feed predicted data for some input model M test. We use our G matrix from, let's say, the final iteration to compute what the data test would look like. Then you plug this test data into this data vector here, and you see what you get out. The test data is just G times M test, so if you plug that in there, you get this expression right here. And then this monster right here we just call the matrix R, or the resolution operator. And so the resolution operator times your input model gives you an output model. And this is one way that we interrogate our tomographic models. So what does this look like? So often we do two kinds of things. In one situation, and this will be done in the tutorial by Jeroen this afternoon, is you put in a checkerboard pattern. So you put some kind of, this is the Earth, here's some checkerboard of slow, fast, slow, fast. It has some characteristic length scale. Here the checkers are bigger than they are here. And then you put that in your inversion, you multiply it by R, and you get some kind of a model out. And you can see here this model is good. You lost some amplitude, but you were able to retrieve those checkers. So yay. And then over here, you put in this model, and you got these checkers out. And they don't even look like checkers, at least in the southern hemisphere. But in the northern, it's OK. And in the Pacific basin, it seems OK. Anyway, you can see which regions of the world are good at resolving that particular length scale of heterogeneity. The other thing you can do is you can put a spike, like a little point, infinitely high point, at this location. Let's say here. This is from a paper that Jeroen published in 2004. And what you can see is how does the inversion spread that out. So in other words, you multiply R by that single spike, and you see how it gets spread out. And here he shows that, for example, in the Indian Ocean, a spike at 550, I think, kilometers gets spread out throughout the upper and even the top of the lower mantle. So this is one way of interrogating that model. How well can you resolve structures in the model? Now, it's really important to remember that this kind of analysis is very limited in some sense. It neglects the errors in computing G of M, because when you computed your test data, you just used the same theory. So as long as the theory was consistent, like this resolution operator analysis won't tell you that your computation of the data was incorrect. It also assumes, obviously, that the data uncertainty is Gaussian, so that there are no real biases in the data. And it fails if the problem is too nonlinear, because, again, it's a linearization around that most likely point, so it might not be very good. So this is something to remember, but we will do this in our practical, because it's still a very useful thing to try. And I want to end by talking a little bit about data themselves. Not all data are created equal for all applications. So if you want to study one quantity, you might want to use the data that's particularly sensitive to that quantity. So often we use these travel times, like in the tomographic problem that I illustrated. And the travel times can be both of surface waves or of body waves. So with body waves, they're called travel times. With surface waves, they're called phase velocities, whatever. However, this kind of data is ill-suited for imaging some small kinds of structures, some structures that geodynamicists and geochemists care a lot about. So for example, here is a figure from Ricker. Here we have a plume, an artificial plume that is like 5% slow in p velocity. It is at some location. It goes through the whole mantle. And if you have perfect kind of illumination, so you put your sources and receivers everywhere and you do a really good job, if you try to image this plume just using travel times, this is what you're going to get. You're going to lose it down here, because your path lengths that sample the structure down here tend to be longer, and so they're going to heal. Those travel times will heal, and you won't see the signature of that plume in the first arriving travel time. However, if you use waveforms, so in other words, if you look at the details of the wiggles of the waves that go through that plume, you will be able to resolve it. So this is just like a basic thing. Waveforms come with a whole suite of other challenges that I'm happy to discuss. But in this particular application, if you're trying to image a small vertical structure that's slow, it's probably better to use something that's not travel times, because travel times kind of heal and they forget about the slow thing they went through if it's small enough. There's another complication, and eventually I'm just going to stop. There's another complication, which is there's going to be a whole bunch of models that don't affect the data that you observe. So in other words, you can vary model parameters in arbitrary ways, which is here represented schematically by this white part. And as you do that, the data doesn't change. And in other words, it's telling you your data cannot tell you about those combinations of model parameters. Those, in terms of inverse theory, we call those combinations of model parameters the null space. It's called the model null space. There's also data null space, which is no matter what model you try, there's going to be data you can't fit. So that part is the data null space. And And this is something to keep in mind, that even if you have great data and you have great coverage, there's always going to be models that your data is just simply insensitive to. So you can always add any amount of those kinds of patterns to your answers and not affect things very much. And it turns out you can map out this data in model null space using what's called singular value decomposition, and we will do that in our practical this afternoon. And I want to, this is my concluding slide, which is just a brief guideline to how we should go about evaluating tomography and, in fact, evaluating an inverse model paper. So there's kind of two conclusion slides. I think you should start by considering the data and the modeling uncertainty to begin with. For example, what is the quality of the data that you're using? What kind of theory is used to predict the data from a particular model? Both of these effects can add up and really introduce uncertainties in your model estimates. The next thing to do is consider how sensitive data is to the quantity of interest. So for example, density is tough. There are modes that are sensitive to density, as Miyake showed, but they're also sensitive to VS and VP. And in fact, in many cases, they're more sensitive to VS and VP. So their sensitivity to that parameter of interest might be low, in which case your inferences of that parameter will be less reliable than in the other parameters. And this posterior model covariance matrix can tell you quite a lot, but be mindful of its limitations. Again, there are these approximations that we are kind of hiding sometimes, where we might have a nonlinear problem that we're linearizing, and we don't always show that this CM is a meaningful representation of the uncertainty of our estimates. And when you come across an inverse model paper, these are various questions that you should ask yourself or ask the author. And if you do that, I think you'll have a much better ability to know which papers to kind of worry about and which papers to worry less about. Although you shouldn't really worry about any science papers. Anyway, I'll end on that, and thank you very much for your attention. Oh. And now I have something to annoy you. This is going to play on loop. These are these model space searches. This is an animation Tolu made. So what we have, I guess, 7 minutes for questions. The bottom is like later on in the chain, so it kind of locks in the parts that are. Is that your question? Or? No, Juan has a question.
Yeah, so you talked briefly about resolution tests,
Mm-hmm.
but I think it was not in either of your two conclusion slides. So I would like if you could comment a little bit on how important they are or not, because to me as an outsider to seismology, it seems like there's always this fight. There's people that includes them, there's people that don't. So how bad is it when you don't include them, and why people do not include them if they are not so difficult to do?
This is a great question. So, the posterior model covariance matrix contains the same information. In fact, you can construct a resolution operator from the model posterior matrix, or you can do it the other way around. So as long as you show one of these, I think it's okay. The question is, I guess, it's really a problem where we have models that have thousands or tens of thousands or hundreds of thousands of parameters. So how do we go about visualizing the trade-offs among all these parameters when it's physically impossible to show them all? So one suggestion is sometimes to show movies of tomographic models as opposed to a single model. You show the whole movie, so you can see what kind of features emerge in those. But that's not really feasible in modern-day publishing. So I think some kind of resolution analysis, be it through a model covariance matrix or a resolution test with input structure, is very useful. But again, for highly nonlinear problems, that's not the appropriate approach, and you should really use a full model space search approach. Now, there is no consensus, as far as I can tell, in the seismic community about exactly how nonlinear our problems are. There are kind of two camps. There are camps that think that they're very nonlinear, we cannot use these linear techniques, and then there are camps that think, okay, well, they're nonlinear, but it's not that bad. So, and I don't know where I stand there yet. I kind of am migrating from camp right to camp left.
Can I make a comment on this?
Yeah.
The forward modeling techniques are very powerful, but they're very heavy computationally, and so right now people make very, very strong assumptions on a theoretical relationship. I mean, basically, most people will do 1D models under different places, which is not necessarily correct from the theoretical point of view. It's very
Which
hard to
introduces
introduce
error.
the whole 3D kind of. So I would, raise a little bit of a caution. I mean, maybe in the future this is going to be resolved, but right now, sampling the space more broadly, which allows you to get away from local minima, is a great idea. But on the other hand, you pay for it by having to use very simple theoretical relationships, which you don't have to do if you pose the problem in terms of an inverse problem and you already know enough about the Earth that you can start close to the real solution.
So Barbara's completely right. So the one thing I didn't mention in Juan's response, which I should have, is that, model space searches can explore the nonlinearity of the problem fully, but they're much computationally more intensive. So that usually means that people will approximate how they do that G of M curve. And of course, as I showed you, that can really mess you up too. So you have to be careful. You have to either choose problems for your nonlinear searches that lend themselves to kind of effective approximations in the forward computation. But if you can't do that, then you should probably just use a kind of an iterative linearized approach. But yeah, it's tough. We'll get better at it. Eric? Okay. Caroline. Thank you for coming just in time for my talk.
Thank you. Yeah, I just have a comment on the resolution test, and do you hear me? Yeah. I just wanted to point out that when you do a resolution test, you just test the particular model that you have put in input, that you use as an input.
Yeah.
And sometimes they can be completely misleading. For example, if the particular model that you have chosen has no component in the null space, you may retrieve it very well. But if the actual model that you are looking for has a component in the null space, you may be completely wrong in trying to, if you did the test with the true Earth. So in fact, as you never know what is the model that you're looking for, it's useful to do some synthetic tests like this, but you have to keep in mind that they just tell you or you recover the particular model that you have put in input. And there are some papers that shows that, for example, when you recover a very small checkerboard test, you can be in a situation if the size of the checkerboard is much larger, you cannot retrieve it at all.
At all, yeah. There's a beautiful paper by Tarantola where, they do a great job here and then they make the boxes bigger and you don't see any of them. So, it's not always that you can see the bigger stuff better than the small stuff. That's a great point. Thank you for pointing that out. And now it's Caroline.
Yes. Is that working? Okay. I just have a comment I think it's important to make. When you mentioned that the forward modeling removes the need to have regularization, it removes the need to have explicit regularization, because you're still going to have implicit regularization through your parametrization. And also, when you do a model space search, you do have to tell your computer code that you look for this parameter within this range, right? You have to put some boundaries,
still have prior.
And that is going, I mean, if the boundaries are very small, it is similar to regularizing the problem around a starting model. Now, ideally, they have to be big, but practically, you have to put bounds. So that is some regularization that you can't really get away from.
That's a good point. Again, don't let people confuse you. Regularization also includes parameterization. It's implicitly there in the parameterization. And the other thing that Caroline points out very correctly is, if you're searching this model space, because you have to do it like before you die, you have to kind of limit the model space in some ways. So you also introduce prior information, like you're only going to look in this region, for example. And so you'll never find something out there because you're not looking there. So that's a great point. Anyone else? Thank you. Okay, well, welcome everyone, or almost everyone, and thank you, the new arrivals, for coming just in time for my lecture. I know that's what I think what many people wish for, like America on her birthday wished to hear a lecture about inverse theory, but KITP was closed, so we couldn't do one. But and I know many of you have wished also to receive an inverse theory lecture for your birthday. But there's someone in the audience actually who gets to get an inverse theory lecture for her birthday, so we can all clap and wish Sana a happy birthday. And of course I did that to give Thorsten time to come back. The lecture today is based quite a bit on the slides that Mark Panning used 2 years ago with quite a few additions of my own. I've tried to make the lecture perhaps less ambitious, so it's not like pulling from the literature to teach you guys things the way that Louise just masterfully demonstrated, but rather it's really to look at the basics and start from the very, very simplest examples of inverse problems to try to draw some, I guess, to build some intuition and make some heuristics for what can and cannot be done in an inverse problem. And hopefully by the end of the talk, if I've done my job right, you will have the tools needed to at least begin to critically evaluate seismic tomography papers or various other inferences, because inverse theories really underlies all inference in geophysics, because what it is it's a combination of approaches that we use in order to determine some physical quantities or physical models given a set of data. This can be done in many ways, but the one crucial ingredient that we must have in order to perform in order to use inverse theory or perform an inversion is we must be able to calculate data or predict data. And in fact, this one fits the data better. But again, the question is, what is really your expectation for the relationship between this dependent and this independent variable? So the fundamental question when we do an inverse problems is this question of parametrization. What quantities or parameters should we consider? Should we search for the slope and the y-intercept of this line, or should we instead search for the parameters that describe this exponential? So like I said, physical models may provide insights into how to parameterize a problem. If you know for sure, for example, let's say that you're measuring the force exerted by a spring, you're stretching the spring, you're measuring the force, you would expect that relationship be linear, at least if infinitesimal strain theory, if the strains are infinitesimal, that's Hooke's law, then you would expect this relationship to be linear. But in some other situation, for example, if this is attenuation and this is temperature, we've learned that this relationship should be exponential. So a physical insight should help you parameterize your problem. However, sometimes physical insight is not enough. For example, if you ask, how does seismic velocity vary inside the Earth? You might not know at what scales it varies. I mean, from what we learned in Louise's lecture, we know that it varies on all scales. So how do you go about parameterizing a problem like that? In that situation, sometimes we resort to preferring what's called the simplest model, the one with the fewest parameters that can still fit the data. I'm using very vague language here, and we're going to become much more precise in our language momentarily. There's something called the law of parsimony, which is actually, it's not the fruit. It's a very useful heuristic. In other words, it's a very useful guideline for how you should approach problems, but it is by no means a law. And in fact, this law of parsimony has led us astray in the past, but I guess the hope is that on average it'll lead us in the correct direction more often than it leads us astray. So the preference for a simpler model is often justified by invoking what's called Occam's razor. And in one paraphrase of some monk's statement, it is vain to do more with more what you can do with less. The more and the with are here flipped. Sorry, guys. So it is vain to do with more what you can do with less. So I guess if you're decorating your house, it'd be complicated. It could be unknown. It could be difficult to quantify, etc. But the but you have to be able to compute G of M. And then, of course, the challenge of inverse theory is to go in this other direction, to close this loop between the two planets of model and data, and to go from the data planet back to the model planet. And the question marks here indicate that I will teach you how to do that. Okay, so let's start with a very simple problem. Let's say that you have a friend who's a geochemist, or you yourself are a geochemist, or maybe a mineral physicist, and you choose to go in a lab, and under some specified conditions, such as maybe temperature or pressure, here are the conditions. It's the independent variable. It's something that you set yourself. Under some pressure or some temperature or some concentration of some chemical, you make some kind of a measurement. That measurement might be the strain. That measurement might be some isotopic ratio, who knows. Anyway, you've done this 4 times because you're kind of, your friend is not so eager, a geochemist, and so she only made 4 measurements. And so each of these measurements represents a pair of quantities. One is the independent variable, and the other is this measured variable, right? This one you set, this one you measure. And what you have to do is you have to think about, okay, well, if I have these 4 measurements, what do they tell me? What am I trying to learn from making these 4 measurements? Am I trying to understand the parameters of some underlying relationship between the independent variable and the dependent variable? And what is that underlying relationship? Well, you might consider, for example, that maybe these 2 quantities ought to be due to some physical intuition that you have built up from your classes in physics or in chemistry. You might think that the relationship ought to be linear. In that case, you would say that what you want to do in the inverse problem is to determine the slope and the y-intercept of this line. However, that might not be the case. In fact, maybe the relationship ought to be some kind of a PowerPoint exponential. Which again doesn't look like an exponential, but M2, and it has a slope which is called M1. And for example, there are some linear problems in geophysics. One of them is, for example, to predict the gravity given the density of an object at a known location. So for example, if you know you have an object somewhere, determining its density is a linear inverse problem. Another kind of a problem might be a nonlinear problem, which tends to be more common. So here I just have a simple one where I have sine, which of course I drew in PowerPoint, so it's not a sine. But it's sine plus some constant equals y. And an example of a nonlinear inverse problem, and we'll get to this in more detail later, is, for example, to predict seismic waveforms given a 3D velocity structure of the Earth. This is a nonlinear, there's a nonlinear relationship between the seismic structure and seismic waveforms. So the way that we typically formulate inverse problems is that we have some observations, and these observations, whether we want them to or not, they're always sampled in time and or space. That's just the way things are. And we usually lump these samples of the data into a vector, which we call the data vector. So that's this vector right here. We usually call it D, and in the rest of this presentation I will call it D. Just to confuse you. The physical quantities of interest, which we also express as some kind of a finite set of parameters that we have to infer. These parameters might define a continuous distribution. For example, the parameters might be the coefficients of spherical harmonics that you've seen before, in which case you could construct the velocity at any point in the Earth given a finite set of parameters. But again, we're determining a finite set of parameters given this sampled set of data. And these parameters we lump into a model vector, which we call M. And then the relationship between the data and the model, so in other words, how you go from being inside, from a model to how do you predict data from a model? We predict it using this function g of m, and I will use g always. G of m need not be linear. It could be a nonlinear function. It could from a known model. So in other words, whatever that model may be, it might be seismic velocities in the Earth, or it might be some geochemical process. What you need to do is you need to be able to predict what you should observe if that were the case, or if that model was known. And the ingredients are usually physics, although not necessarily, and that's not meant to be a joke. We usually define the forward problem using physics, but sometimes we don't know what the physics is. And then we have a variety of approaches, and this is especially true if you want to go work for Google or for other kind of information, big data companies. They often have to figure out what their model is given the data, so they can create these generative processes that can produce data from through an unknown model. Essentially, the machine learns on its own how to predict data. We usually use linear algebra. Again, we don't have to. But what we use it for is to map between the model and the data domains. So what I would like for you to think is I would like to think of kind of like two planets. One planet is the model planet, and one planet is the data planet. And what we're interested in is going between these two planets in an efficient way, so then we don't die in between. And sometimes, although probably we should do this always, we should use probability and statistics to try to quantify uncertainty of our physical model determinations. In other words, it's not so meaningful to just know that I have a particular model. It's much more meaningful to think about how certain the various model parameters or model quantities are. And in fact, we cannot do hypothesis testing if we don't place uncertainty estimates on our models. Because that's just the way it is. So I'm going to get back to this topic of types of forward problems, but here I just want to illustrate a very simple pair of forward problems. In one on the left, we have a linear problem, a simple a linear relationship between quantities x and quantities y. And this linear model here has only two parameters. It has a y-intercept, which is here called